So one of the things I wanted to show you was this. After lecture last time, we went through and discussed what would our schedule be for the next few weeks. You all agreed that we should have a deformables lecture first. A deformables lecture, so we're going to do that today. So I have a quiz for mechanics and materials posted today, and we're going to close that next week. So you all have a week to do that. Afterwards, y'all wanted to do some soils, so we'll do geotech. Now, last year I did the geotech in 2 parts. I think what I'm going to do this semester is try and combine that a bit, try and find the stuff I think is relevant to both, and try and do that in a single lecture as much as possible. Then we'll do some water stuff. Now, on October the 2nd, I'm not going to be here. Okay, I'm going to be out of town. So that lecture, I'm going to have to record in advance. Now, we had scheduled to do probability and statistics. We may want to change that. That is dependent on you, like if you want me to do the ethics lecture or something online, whatever makes sense. We'll discuss that later, but I just want you thinking about that. If there's a topic that you don't feel like you need to be here for, something you could watch online, which of the topics would you pick? So just something to think about. But today we're going to get into mechanics of materials land. I've got 6 problems for you in class, but these 6 problems I think cover mechanics of materials about as closely as possible. Okay? Now there's a lot of topics on here. Some of them I'm skipping. And so for instance, I'm not going to do shear and moment diagrams. Okay? I'm not doing shear and moment diagrams because we're going to beat that into the ground later with statics or structural analysis or, with whatever way we do that. You all, I think, are good there. I'm not going to do plastic deformations because a lot of that revolves around things like plastic moments. And for those of you that had me for steel design, you know what I'm talking about. So we've done that stuff before. If you had me for concrete design, ASFYD minus A over 2, we're talking about. So I think we cover that in other areas. What I'm focused on are the things that are unique to Engineering 216. So I'm talking about axial stresses and deformations. I'm talking about torsion. I'm talking about Moore's circle. Buckling. Even though buckling shows up in steel design, I do want to give it its time in the sun. And things like radius of gyration, things like that. Hi. Okay, so with that, let's just go ahead and get right into it. Okay, so I have a 10 kilogram axial load, which is uniformly carried by an aluminum pipe with an outside diameter of 10 centimeters and an inside diameter of 9.6 centimeters. Now, right off the bat, you're like, wait a minute. This is metric. We're civil engineers. We don't believe in metric. Let me be clear. Just because you're civil engineers doesn't mean that you won't experience metric on the exam. The way that NCES works, they try and skew towards metric as much as possible. Now, they will allow U.S. units in areas that it makes sense. Like, for instance, a lot of the structural stuff is all in U.S. units because, square root of FC prime. That really only makes sense the way that we use it if you use PSI. Remember, you put in PSI and you get out PSI. There are metric equivalents, don't get me wrong, but it tends to follow unit conversions a little better in U.S. units, and so a lot of the structural stuff will be. That being said, fluids might be in purely SI, and this is a section that might be in purely SI as well. So this review is actually in SI. Now, because of that, one of the things that I like to do right off the bat when I do these problems is I like to declare at the beginning what my unit system is going to be and then make sure everything is converted into that unit system. That is one thing that's advantageous towards metric. Okay, bless you. So I have a 10 kilogram axial load that's carried by an aluminum alloy pipe. The pipe is 1.2 meters long. Now I got Young's modulus at 75,000 megapascals. Neglecting the effects of buckling. How much is the pipe compressed? Bless you. Oh, must be the allergy season or something. Now, right off the bat, one of the things that's going to give us probably a hiccup is just the unit conversions, because you can see choice A and B are very, very similar. What I'm going to do is pull up my notebook. Go away. So I screen captured all the problems here, so this is the same thing. Right off the bat, like I said, I'm going to declare my unit system. Now, when you're talking about mechanics of deformable bodies, the base units that you really care about are force and length, because everything else derives from that. Okay? So, for instance, what is stress? Stress is force per unit length squared, right? So as long as you define those, you're good. What is a deformation? It's a length. What is a strain? Well, strain's unitless, so it doesn't really matter anyways. So as long as you have your force and your length units defined, you're good. So what I'm going to do is I'm going to say that force is going to be measured in newtons, and my length is going to be measured in meters. Okay? And so that's going to yield a stress unit in newtons per meter squared. And so what is that? That's pascals. You could say kilonewtons per millimeter squared and deal in things like megapascals, but I'm not going to worry about that. Okay. So let's make sure that everybody's crystal clear about what's going on in this problem. We have some pipe that's being compressed. And when it's being compressed, mechanics of deformable bodies tells us that that thing will squish. It will get shorter. Right? And so what we're after is that deflection. That's what we're after. How much does this thing compress? Now, does anybody remember what is the fundamental expression for if you have an element that's being loaded in axial fashion, either being tension or compression? If I take that and I squish it or I stretch it, how do I determine how much it has extended or compressed? Anybody remember how to calculate that? The formula should at least be somewhat familiar from what we did in structural analysis with trusses, but it's a fraction, and it's PL over EA, right? So we take the axial load, multiply it by the length. We take the Young's modulus multiplied by the area, okay? And so if you recall, one of the reasons when you, I mean, at least when I taught the course, for axial load, right, the amount of stretch is PL over EA. And then for torsion, if you take TL over GJ, right, that'll give you the total angle of twist, right? So you take a member, you yank on it, it gets longer. You take a member and twist it, it rotates, okay? But it's all acting along the axis of the member, which is, if you look at these expressions, they're very similar. We have the applied load, the member length, a material property, and a cross-sectional property, okay? That's why those two topics go hand in hand quite well, okay? That's why usually you cover axial loads and then you cover torsion right after, because it might not seem like they're related. Take a member and yank on it, twist it, but the math actually works pretty well. All right? So let's see if we can determine some quantities right off the bat. So let's see. We're trying to determine how much is the pipe compressed. So we're going to need a P, an L, an E, and an A. We're going to need this in order to determine this quantity. So does anybody know one of these right off the bat? E. Okay. Now this is 75,000 megapascals. Okay. Now here's the thing. That's megapascals, but our base units up here on the top are in pascals. Okay. So this is how I deal with this. What does that letter M mean? It means 10 to the 6th. So just replace that as 75,000 times 10 to the 6 pascals. So this becomes that. They're the same thing. What else do we know right off the bat? the length. The length is 1.2 meters, and that's fine because that's in the appropriate unit system. Okay, what about P? Do we know what P is? Say it again. Say it again. There you go. The 10 kilograms that's a mass, right? We need that load to be expressed in a force, right? So what I'm going to do is I'm going to take that 10 kilograms, multiply it by 9.81 meters per second squared, and so that's going to give me 98.1 newtons, right? So just keep that in mind, okay? This is the type of stuff that can happen on the exam. They give you a mass, you need a force, you got to multiply it by gravity. Very common little, I don't want to say trick, but it's a detail that you need to keep in mind. Now the area, let's think about that one for a second, okay? So let me draw this down here. We have a pipe, and that is the best drawing you're going to get. So that has an outer diameter of what? 0.1 meters, and an inner diameter of 0. Well, here, let's do this. So 9.6 centimeters or 0.096 meters, right? Again, convert. So how am I going to determine the area of that pipe? Remember, when we say area, this is what we mean, okay? Remember what we think when we think cross-sectional area. Okay, this is how I define it. Samurai sword or lightsaber, right? Then imagine taking that member, sticking it in a bucket of paint, and then sticking it on a piece of paper. What's the piece of paper going to look like? It's going to look like this little ring, right? And so how do I determine the area of that little ring? It's the area of the big circle minus the area of the little circle, right? Make sense? So this is going to be pi over 4 outer diameter squared minus pi over 4 times the inner diameter squared. Or I can just factor out the pi over 4. So, actually here, let me use some brackets. So, 0.1 meters squared minus 0.096 meters squared. And so this might be a small number, and that's okay, because what we're talking about is square meters, and we're talking about a pipe that's that big, so it's going to be tiny. That's fine. Excuse me. Say it again.
6.16 times 10 to the negative 4.
That's in square meters. Do I have a second on that? Okay. So therefore, delta is going to equal 98.1 newtons, 1.2 meters, 75,000 times 10 to the 6 pascals, 6.16 times 10 to the minus 4 square meters. And so what does that come out to be? So I'm just doing PL over EA, just this expression here. 2.6 times 10 to the minus 6. Do I have a second on that? What are the units for that? Meters. So if I want to turn that into millimeters, what would that be in millimeters? Say it again. Think about like this. To the negative third, right? because 3 meters is 3,000 millimeters, right? And so, bless you. How do you get that conversion? You multiply by 1,000. So if I got 10 to the negative 6 and I multiply by 1,000, I'm taking that down 3, so it's or adding 3 to that, so that's minus 3. So how do I write that in decimal notation? Well, I go 1, 2, 3. So that's 0.0026 millimeters. What do you think?
Anytime we hear axial, we're going to look for this formula.
This formula will basically relate anything that you need. And so let's talk about that real quick. Can I erase this? Watch this. Okay? So, okay, watch this. All right? Would you agree with this? Would you agree with that? Okay. Would you then agree with this? Right? So let me just flip that around. So P over A equals E times that. What is this right here? Now what is that? That's the change in length over the original length. So from that equation, you can determine stress, strain, everything in between. The one thing that's a little tricky, and this is meant to be a fundamental review, so I'm sort of skipping over this a bit, but the axial load in this problem is constant, okay? The section properties are constant. As a result, you do not need to apply integration, okay? So technically, can I erase this? Technically, what you need to do in order to determine the displacement is you need to integrate the axial load and the area. But if that's constant and that's constant, the integral of this from 0 to L is just L. Okay? Does that make sense? Now, this is just a fundamental review. So, any questions? All right, let's go on to the next one. All right. Okay, right off the bat, before we even do anything, I'm going to do the same thing on this problem. I'm going to say that force is in newtons and length is also in meters. Okay, so stress, what the? I can't spell today. Stress is in pascals. Okay. Now this problem is a little different. Okay. Instead of this problem being an axial load where it's PL over EA, this one is a torsion problem. I have a steel pipe fixed at one end with a torque of 100,000 Newton meters. The pipe is originally 3 meters in length, and has an outside diameter of 35 centimeters and a wall thickness of a single centimeter. Now, steel has a modulus of elasticity of 210 gigapascals and a Poisson's ratio of 0.3. What's the resulting angle of twist? Okay, so right off the bat, because they're asking for the angle of twist, the governing equation is going to be, sorry, I'm getting ahead of myself, going to be TL over GJ. Okay, all right. And some of these parameters are going to be pretty easy to find. So I have the torque, which is 100,000 Newton meters. So that's the load. I'm taking it and I'm twisting it with that much torque. And then it originally has a length that's 3 meters. That's pretty easy. The other two properties are what take a little bit of work. Okay? Now, let's take them one at a time. Let's start off with G. Okay? Now, G is the shear modulus. Okay? And so what do I mean by the shear modulus or the elastic modulus? Okay? What is E? E, or Young's modulus. E is the slope of your stress-strain curve in the linear region. But basically, it's just an infinitesimal measure of if I apply stress and get a resulting strain, what's the relationship between those two, right? That's what that is. Now, E, I'm using the board here because I don't have much room on the screen, but E is an expression of normal stress and strain. In other words, if I take an element and I squish it, it gets thinner, right? And so E represents a relationship regarding normal stress and strain. Normal stress and strain mean pressing on it, right? G, however, is about not normal stresses, but shear stresses. So meaning equal and opposite directions. So if I take an element and I shear it, what happens? Sort of looks like that, right? Okay? Here, I've got normal stress and normal strain acting up and down. What is strain? Remember, normal strain is sort of like a percent change in length. Like the change in length over the original length, it's a percent change. Here, we've got a shear stress, a shear modulus, and a shear strain. And in this case, the shear strain is that change in angle. Y'all remember that? Okay. So the question becomes, how do I determine G if all I have is E? Well, you can't do it with just E. You need another property. What's that other property? Poisson's ratio. Does anybody remember what Poisson's ratio is? Like what it actually means? That's okay. That's what we're here for. So you have an element and you squish it. What happens? It gets shorter. But what else happens? It bulges out, right? So in reality, it does that, right? Imagine the other way around. Imagine you got a piece of taffy in your hand. You take that taffy and you stretch it. It gets longer, but what else happens? It gets thinner. Poisson's ratio tells you the relationship between those two. So if I take a piece of steel and I stretch it, it gets about, it gets thinner and it gets longer, but the ratio between those two is about 0.3. In other words, its strain this way is about 30% of its strain that way. That's what Poisson's ratio is, and that's a material property. Okay? Now, there is an expression in the world of mechanics that says if you have E and you have your Poisson's ratio, that will tell you what the shear modulus is. And if you don't remember that, where do you find it? There you go, the reference handbook. So So go to mechanics and materials, shear modulus. Bam, right there. Okay? So I'm going to say 210 gigapascals over 2 times 1 plus 0.3, and I'm going to get what? Do I have a second on that? And then the giga is just 10 to the what? There you go. All right. Now, so we got T, we got L, we got G. What about J? Okay. Now, first off, I'm going to tell you right now, if you're doing a torsion problem, you will always be dealing with a cross-section, at least on this exam, that is circular. In other words, when we twist something, we want it to be circular. Why? Anybody remember why? Non-circular cross-sections like to do something. Anybody remember? What's that? No. Non-circular cross-sections like to do something called warping. Okay? When you twist something that's circular, before and after, it remains plane. But if you were to twist something that's non-circular, like let's say I have a shaft and I twist it, what happens is it actually goes in and out of the plane. So if I have something connected over here, it's actually going to butt into it. It's why, and so that's one reason. But another reason is just anything that's being twisted, the most efficient shape possible is a circular cross-section. It's why if you look in automobiles or really any machine that's got something that's being twisted, it's circular in one way, shape, or form. It's the most efficient use of that section. Also, if something's spinning, it makes sense that it's circular as well. Okay. Now, if I have a circular cross-section, I need to compute this property J. What is J? Well, J is it's a polar moment of inertia. It's a torsional constant of a circle. How do I determine that? Well, that's a good question. Now, I remember the formula, but you may not. Okay? And if you don't remember the formula, that's okay. That's what the reference manual is for. Okay? Now, first off, right off the bat, there's this. There's J. Now, as for where this property is, I'm wagering, and this can change, I think, but I'm wagering it's in mathematics. Let's go into mathematics. Or maybe it's in statics. There we go. So right off the bat, if there's any properties that you don't remember, the statics section will list properties of, like for instance, here's a circle, what's A, if here's a pipe, what's the area, and so on and so forth. Looking at a circular cross-section or looking at a pipe, here's J. Okay? Now, the way I always remember J is pi times the diameter to the fourth over 32, or pi r squared over 2. So, but if you don't remember, that's fine. That's what the manual's for. So J for a circular cross-section is pi r squared over 2, or pi d squared over 32. So I'm getting that directly from the manual. Now because we have a pipe, what we're going to do is we're going to take pi times the outer diameter to the fourth minus the inner diameter to the fourth over 32. Is everybody okay with that? Now, let's see if this makes sense. What's the outer diameter of this pipe? I'll deal with the units here in a second. We'll deal with that in a second. What's the outer diameter? What's the inner diameter? Say it again. 33 centimeters, right? The outer diameter is 35 centimeters, and the wall is 1 centimeter thick. So here's the outer diameter to get to the inner diameter. Outer, one wall, another wall, right? So what we're going to have is we're going to have pi 0.035 meters to the fourth minus 0. Whoa, my goodness. What's that? In the meters. Yeah. Sorry. And then this is 33 meters to the fourth. What, did I do something wrong?
It's not millimeters, it's centimeters.
Oh. So this is 3.5. Sorry. Mistake counter doesn't apply in. See, I'm telling these jokes in structural analysis this semester, and they're so quiet. I'm like, guys, it's okay. You said the microphone was sketchy. Is that a good thing? Right? Oh, for God's sakes. All right, so what does this come out to be? It's going to be tiny.
3.09 times 10 to the minus 4th.
That's meters to the fourth. Do I have a second on that? Okay, good. So TL over GJ, let's put this down here. And so I'm writing a little sloppily, but all the values are right here. Ooh, minus 4. Now, keep in mind, you're calculating an angle of twist. One of the things about this formula, and this is the case in a lot of mechanics-based formulas when you compute angles, if you just plug and chug and don't consider units, the answers come out in radians. Because remember, mathematically, radians are a unitless means of expressing angles. Okay? So just keep that in mind. Like for instance, in structural analysis, when we did slopes and rotations of beams, it really was unitless. We had to apply that 180 over pi to get it into degrees. So I'm just wanting to throw that out there. And so what does this come out to be? 0.12. And since the units are unitless, this is radians. Bless you. And you can follow the units because on the top we have newtons times meters squared, and on the bottom we have Newton over meters squared times meters to the fourth. So that's Newton meter squared, Newton meter squared. They all cancel. Okay. Sound good? All right. Can I erase this on the board? Now, when I teach mechanics of materials, we spend a vast amount of time in the course covering what I call the big four stress formulas. Okay? So the first one is the axial stress formula, which is just sigma equals P over A. Okay? And from that, you can get delta equals PL over EA and stuff like that. The second is torsion. And so torsion tells us that the shear stress is TR over J, right? So that's the fundamental formula for the stress due to torsion. Okay? There is a third and fourth related to bending and shear. Okay? The bending one, I don't care what you feel about Engineering 216. You saw that in some of my classes. Sigma equals my over I. That's a big one, right? And we did that in concrete and steel and you name it. The last one for shear, transverse shear stress, VQ over IB. That's your fourth fundamental stress formula. Okay? Those are the four fundamental formulas to determine stresses in skeletal structures. And then, I mean, the whole point of mechanics of materials is to try and determine what those fundamental stresses are, and then what happens if you have multiple stresses combined together. Okay? All within there's this thing called buckling at the end. So that's Engineering 216 in a nutshell. So each one of these problems sort of relate to that. An axial, a torsion, a bending, a shear, then we have a Mohr circle problem, and then buckling. And that's this review. Okay? So this problem, we have a beam with a triangular cross-section. What is the maximum compressive stress in the beam? Okay? So if this is problem 1, this is problem 2, this is problem 3. Okay? So sigma equals my over I. Bless you. All right? So in order to do this, we need 3 quantities, m, y, and I. Okay? So let's take this one at a time. I have a simply supported beam subjected to a uniformly distributed load. So, I mean, if you all don't recognize this, I'm going to be sad. Right? We've got a shear diagram that goes up, down, up, right? That's the shear diagram, and then the moment diagram. Lot to a little, little to a lot, right? Does anybody remember what that formula is? How do you determine the maximum bending moment in a beam with a uniformly distributed load? There we go, WL squared over 8. That is right. It should have been like a chorus of voices from everybody in the room. Just, you know.
We knew Austin needed the help. We let him do it.
I mean, it's like, hold on. It's like P over gamma plus Z plus V squared over 2G. Oh, the structural engineer, remember Bernoulli's. Marker drop. Because I'm not dropping the mic. It's expensive. My goodness. Okay. All right, so I'm going to erase this. So right off the bat, up top, we know that, okay, I'm going to do the same thing. Force is in newtons, length is in meters. Okay, and so what are our fundamental formulas going to be? Well, we know that sigma is my over I. We know that. And so what else do we know? We know our m max is going to be WL squared over 8. That's easy, okay? That's easy. All right, now what about the moment of inertia and y, okay? Let's take this one step at a time. Let's start off with y. Does anybody remember how you measure that y term? Off from the bottom. What do you mean by middle? The centroid. You were right, yeah. But the term middle being the centroid, okay? Now, let's take a look at this. I have a section, a cross-section. If I samurai sword or lightsaber through this beam, it looks like this, right? Okay? Where is the centroid of this triangle if this is H? Where? Third of the way up. That's the centroid. Okay, so I measure y from that point. Okay? Now what's the problem asking for? Okay? The problem is asking for the maximum compressive stress in the beam. So how do beams bend, right? This beam's going to bend what, like smiley face or frowny face? So which side of the beam is experiencing compression, the top or the bottom? The top, right? So that y distance should be the distance from the centroid to the extreme compression fiber. So if this is H, what's Y? 2/3 H. It's not 1/3 H, it's 2/3 H. Does that make sense?
Hold on. There's a tensile fiber and compressive.
Yes.
Why are we using? Because it says.
It's asking for the maximum compressive stress. So if a beam, here's the beam, right? And it's wanting to smile, right? So magnified, the beam looks like this. So if here's the centroid, I want the distance from the centroid to the very, very, very tippy top of the beam. If it was asking for the extreme tensile stress, I would go from the centroid to the very bottom, right? Make sense? And so for a triangular cross section, that Y is 2H/3. Now, the last thing is the moment of inertia. What's the moment of inertia of a rectangle? Ooh, that is not right. BH^12 is, no, hold on. Sorry. BH^12 is the moment of inertia of a rectangle. What? Here, what's the point? You're guessing. And here's the thing. When I was setting up this problem, guess what? I didn't remember it either, right? But do I need to remember it? There you go. We got the reference manual. So let's go back to that. We're in the statics section. Circular sectors, parabolas. Maybe I need to go up. Boom. So triangles, what's the moment of inertia? Now remember, when you're looking at mechanical properties for mechanics, you're worried about centroidal properties. So if I have a triangle, the centroidal moment of inertia, whether I'm looking at this, what have you, is BH^36. Okay? So we have that. I is BH^36. So we got everything we need to chug out this problem. Everything's right there. Sigma equals my/I, and that's how we're computing each of those terms. Pretty simple. So I'm just going to start plugging and chugging, because at this point it should be pretty boring. So W is 80 newtons per meter. L is 10 meters. So from those two, M is WL²/8, which is 80 times 10 meters. Don't forget to square that over 8, which is, so 80/8 is 10, so that's 10 times 10 times 10, so that's 1,000? Is that right? So that's 1,000 Newton meters. So sigma equals my/I, check on the M. What about the Y and the I? Well, here's the thing. One of the things that we were not given about this triangle is its height. Okay? Here's the triangle, and, oh, that is a little too pronounced. So we know that, and that. We know that this is 12 centimeters, and we know that this is 10 centimeters, and this is 10 centimeters. But we don't know the actual height. Well, what we do know is that if we cut that right smack dab in the middle, this is 6, and this is 6. If we cut that right smack dab in the middle, that makes that a right angle. So if that's 6 something and 10, what's that something? 8, right? Because it's a 3, 4, 5. So this height is 8 centimeters. So the height is 8 centimeters, or 0.08 meters. And then the base is 12 centimeters, or 0.112 meters. And so from B and H, I can get that y is 2h over 3, so 2/3 of 0.08. And then I is BH cubed over 36. So okay, so what's y? That was that 0.53 or 0.533? So 0.0533 second on that. And then this one, that's going to be tiny. That's
1.71 times 10 to the minus 6 meters to the 4th.
boom. So therefore, maybe just do this in a different color ink so it sort of summarizes. Sigma equals, we have 1,000 Newton meters. We got 0.0533 meters, and we got 1.71. Here, I'm going to scroll down a bit because that's being, whoa. Come on. Oh, for goodness sake. You know what? Let's just rewrite it. You want to be that way? All right. So sigma equals and what does that come out to be? Should be pretty big. Because you're dividing by a really small number.
3.12 times 10 to the 7.
Pascals, right? So that's 3.12 times 10 to the first megapascals, or 31.2 megapascals. Difference just being rounding. Everybody's laughing. How we feeling? What? What? What'd you say?
I said the answer's not up there, so we just have to skip it.
Oh, no, that's rounding. In fact, one of the things, and I probably should have reworded this on this question, the name of the game on the exam tends to revolve around the term most nearly. It'll say what is most nearly the answer, and that's realistically what you get on the exam. Like a lot of these problems I write because I know what the answer is, but a lot of times on the exam, different students will do the problems in different ways. Doesn't mean that they're doing it incorrectly. Some students will calculate intermediate values and then take those values and chug something else. There are some students that will derive all of this in one big equation and plug and chug all at once. Because of that, they say most nearly to try and avoid, like, well, he or she got it wrong because they didn't round correctly. That's not really what they're after. Yes?
So if we have a brain fart and can't remember the max moment formula to avoid having to go through the shear and the moment diagram, is there a table kind of like was in the skill manual that covers that?
Actually, no. Let me clarify. So if you go, like, what there is are slopes and deflections. But remember, you can always samurai sword or a lightsaber, and you can always draw the shear and moment diagram. Don't worry, we'll get experience drawing the shear and moment diagram. That should be like so easy, you know, because you had the best teacher ever.
Is that why they don't give it to us? Because they want us to have to find
Yeah, but let me say this. What they won't do is give you this problem with a beam like we had on our first structural analysis exam, where it's like super complicated and all that, because the point of that exam was to teach you how to draw shear and moment diagrams. If you have a problem where you have to determine the moments, it's pretty simple. Like, for instance, if you have a beam that's like this, and it has a load on the end, you don't need to draw a moment diagram in order to determine what is the maximum moment and how much is it. It's right here, and it's P times L. That's it. Because you can just cut a section and look, P times L. So if you have to do that, the analysis will probably be pretty basic, because the point of the problem isn't really so much the structural analysis, it's this. Does that make sense? Now, if you were doing the PE exam, there's a possibility that it gets a little bigger, but by then you're doing this stuff all day, every day, and it's not as bad. All right. Does that make sense? Any questions? Okay. So we have 4 fundamental stress formulas, and we've had one problem on each of them in one way, shape, or form. Axial, torsion, bending. What about shear? Hold on, I have a rectangular beam that is 4 centimeters wide and 6 centimeters high, and is subjected to a transverse shear of 7,000 newtons at a particular location. Doesn't really matter where it is, because you just need to know what the shear is. The beam is constructed of 2014-T3 aluminum. We'll get to that here in a second. What is most nearly the maximum shear stress at this location? Okay, so whenever you have a beam, that beam, when it's subjected to transverse loads at any random point, could have a shear and a moment, right? It's why you have a shear diagram and a moment diagram. Forces and external loads on structures cause stress. It's as simple. So at any random point, if you have a shear and a moment, you could have a shear stress and a bending stress. Okay? So the bending stress is computed using sigma equals my over I. The shear stress is computed using the following formula. Tau equals VQ over IB. Okay? Now, most of this is pretty plug and chug. Okay? The V is 7,000 newtons. The B is going to be the beam width. So if you have a beam, right, and it's got some loads on it, right, and you samurai sword or lightsaber through that beam, so let's draw it in 3 dimensions, and you samurai sword or lightsaber through that beam, so here's the beam, right? There's the cross section that you're cutting through. That dimension is B, the width of the beam at the cut. Okay? So how wide is the beam at the cut? It's 4 centimeters. Okay? Now, while I'm at it, I'm going to go ahead and do the height. Because I do need the moment of inertia. Now, what's the moment of inertia of a rectangular cross-section? BH cubed over 12. No. Sorry. Yeah. But let me be clear. That's the whole point of us doing this together, is to shake off the rust, if you will.
Should we do this in centimeters since all the answers are in centimeters?
Oh yeah, I guess we should. Yeah. See, I'm just. But let me also say this: because all the units are the same, like really all we're going to get is the value answer. So let me. Thank you. I wasn't even looking at that. It's like, that's what you get for the whole BH cubed over 12 thing, Dr. Mike. I'm going to call you out on your mess. I'm just messing. All right, 4 times 6 cubed over 12 is what? 72 centimeters to the 4th. Okay. Now, first off, I want to make sure that everybody is clear as to where shear stresses come from. I'm going to borrow your notebook. No, actually this one. I need something with something I can bend. Okay, so what's happening with shear stresses is as follows. So here's a beam, right? If I bend that beam, it's fairly easy to bend. Okay, why is it easy to bend? Because this isn't one beam. It's 100 really tiny beams. Okay, each one of these. I'm sorry. Sorry. Each one of these pieces of paper is an individual beam, okay? This is really one of those greater than the sum of its parts things. And what I mean by that is this. Imagine if I had a lot of time on my hands and was really bored, and I decided to glue every one of these pages together, okay? Instead of bending 100 sheets of paper, I would be essentially bending one solid block of paper, okay? And that would be a lot tougher to do, okay? The reason why is this. When I bend these papers, when I bend this notebook, what's happening to the papers? They're just freely sliding, right? It's why here they're flat, but when I bend them, see how they're like separated from one another? When you have a solid beam, those internal layers, they develop stresses in between them, okay? That's what the shear stress is, that's where it's coming from. Okay, I'm done with your note. I won't drop anything more, I promise. So the shear stress is acting in this direction. The fibers in the beam are wanting to split apart this way, okay? So the way that we determine these shear stresses is we're basically trying to find what is the shear stress at a given location. So what we're trying to ask when we do shear stresses is what's the shear stress here? Or what's the shear stress here? Or what's the shear stress here? The shear stress changes as you go up and down. From here to here, it's the same. So to take the notebook analogy, if I take the notebook and bend it, it doesn't really matter if I'm looking at the top of the page or the bottom of the page. The shear behavior is the same. All the pages just sort of go along the same direction. Doesn't matter from left to right. What matters is from up or down. In other words, if that's a notebook with 2 pages in it or a notebook with 200 pages in it, it's going to behave a little differently. Make sense? Now, I'll go ahead and tell you that if you have a beam, right? There's its centroid. Remember the shear or the bending stress profile looks like that. The shear stress profile looks sort of like that. And the maximum shear stress is in the middle. And so that's sort of opposite from bending stress. Remember, when you have a beam and it's being bent, the bending stress at the centroid is 0. But with shear stress, especially if it's symmetric, the shear stress at the centroid is the maximum. Okay? So what that gets into is how to compute Q. Well, the way that we compute Q is this. Here's the beam. This is 4 centimeters. And so this is 3 centimeters, 3 centimeters. The way that we compute Q, the term Q is basically a first moment of area. Okay? So we look at everything above that line of interest and we say, okay, let's look at this area right here. What's the area of that block? 12 square centimeters. What's the moment arm? And the moment arm, what I mean by that is how far is it from the center of that to right here. What is that distance going to be? 1.5. And so therefore, Q is A times Y. Right? So if here was my cross-section, there's my centroid, and I wanted the shear stress right here, it would be that area times that distance. If I wanted the shear stress here, it would be that area times that distance, which is why it's the biggest at the middle, okay? Because it's the biggest area and it's the biggest area. So therefore, tau is VQ over IB, which is 7,000, 18 cubic centimeters, 72 centimeters to the fourth, and 4 centimeters. And so what does that come out to be? Most nearly, so 440. But wait, Dr. Mike, what about this crap right here, the 2014 T3 aluminum? It doesn't matter. In seriousness, it doesn't matter. And let me tell you why it doesn't matter, okay? Can I erase this? Okay. Okay. So mechanics of deformable bodies in general can basically be a journey from forces and loads all the way to deformations. And we make a couple pit stops along the way. What do I mean by that? Well, if I have some forces and loads, I can take those forces and I can determine stress. Okay, so how do I determine stress? Well, it's usually something like sigma equals P over A. I probably have to do some structural analysis and so on and so forth, right? So it's a function usually of statics and the cross section. What do I mean by that? Well, yeah, so if I have sigma equals P over A, so I take the force divided by the area. The bigger the column gets along its cross section, the lower that stress is, right? So there's that. What I then say is, okay, if I got stress, I can then say, what's the strain? Now, how do I get from stress to strain? What do I need? You're both basically saying the same thing. You need material properties. In other words, if I apply stress to a beam, a shaft, whatever, how it responds, how much strain it develops, and how much resulting deformations I get is going to be a function, ultimately, of what the material is. In other words, if I apply stress to a concrete beam, I get a different response than if I apply stress to a steel beam. Make sense? This problem said, here's some forces, what's the stress? So I don't need the material properties at all in order to get there, right? It doesn't matter if the beam's made out of 2014 T3 aluminum or steel or concrete or wood or whatever. It doesn't matter. It only matters when the problem says, what's the strain or what's the resulting deformations and what have you. That's what matters. Now, how do you get from strain to deformations? All honestly, it's the geometry and the member length. Usually about the simplest way to put it. Compatibility. So we have fancy names for this. We call this equilibrium. Whoop. We call this compatibility. And we have a real fancy name for this. Constitutive relationship. Basically Hooke's law. So what's that? No, I heard you. I'm just like, no, what was that? Just to make you, acknowledge that. Gotta get my structural analysis class laughing like this,
I can't believe they don't.
I know.
It's so sad.
Well, they had Jews, so they don't get the toll.
There you go. There you go. Maybe it's the shell shock. That's what it is. Okay. Everybody good? All right. Here's the thing. All you need to know is this. You got your karate chop. You got your Judy chop. And you got your ninja chop. Now don't go karate chopping while you're kung fu kicking. Because there goes your leg. And there's not much use for one-legged ninja. If you don't get the reference, look it up. That is a meme before memes were a thing. That's an old. You get the reference, right? Okay. Okay, that's like that's like undergrad for me. So stop talking. That's first grade for me. I'm just messing with you. I'm just messing with you. It's hilarious. Oh, man. No, that actually is pretty funny. I'll give you that one. Okay, so let me, look, this is a review, but it's also sort of a means of trying to cover some stuff that I think is pretty important. So in all seriousness, I want to explain what's going on with this because, look, one of the most tricky concepts that I think engineering students have, and to be honest, I don't think it matters who you had for the class or what you covered. This is difficult. It's always a little esoteric. It's always a little out there. And so I want to talk about Moore's circle. Okay? I think that a lot of times students think Moore's circle and they're like, I didn't understand anything about that. But I knew there were some formulas and you plugged into that, you got some numbers, and I got through the class. And so I want to try and remove the mystery from that because it's really not that complicated. And I was joking a bit with the whole Judy chop and ninja chop and stuff like that. But in all honesty, here's what Moore's circle is. Okay, you have an element, and it's being subjected to loads and this. It's being twisted and whatnot. And up until now, what we've been saying is when we do our samurai sword, we've just been doing it perpendicularly and cutting straight through because it seemed like a natural thing to do. We cut a section and we say, okay, what's the resulting stresses along that section? Okay? But when you have a member that's being twisted and bent and sheared and yanked on and all this different stuff going on, maybe that's not the right way to do it. Maybe instead, what we should do is cut it at an angle. So the joke is instead of Judy chopping, maybe we ought to ninja chop. Okay? Now, what is Moore's circle? Moore's circle is just a shortcut graphical way of expressing how the stresses change when you cut at an angle. That's it. That's all Moore's circle is, okay? And so the way that we formulate that from a mechanics perspective is I can take some state of stress. So I have an element. What's the stress this way? What's the stress this way? What's the shear stress? And I can say, well, what would a new stress state be if I took my coordinate system and I rotated it 20 degrees or I rotated it 30 degrees? What's my new stress state? Okay? There's a video that I show in Deformables. I'm going to see if I can find it. Hold on. If I can't find it, maybe I'll go to one of my videos and pull it up. Hold on. Now we're getting desperate. And hold on. We're going to turn the sound off because I can't stand the sound of my own voice.
Wow.
Well, I can't. There's that dorky dude. Here we go. Is this like Inception? do I need the boom? The sound?
This is what you post to the
Yeah.
videos at the end.
This is how you know you made it.
Wait, hold on.
For yourself.
There we go. It's this one. Here we go. We'll find it. Hold on. Yeah, I'm recording YouTube right now, and we're watching a YouTube video of watching a YouTube video. That.
And YouTube will say you're illegally recording.
No, yeah, I'll start getting copyright claimed on myself or something. All right. This is awesome. Folks at Google are like, what's going on? Okay, so what I want to show you, what I want to show you is this. So I have this video of a stress state, okay? And so imagine what happened was, you know how to compute axial stresses and torsional stresses and bending stress and shear stress. That's what we've done on these problems. So let's say we have an element that's got a bunch of different stuff going on, and so these are the stresses, okay? So here's the stress state, and we determine that stress state by just cutting at a perpendicular angle. So what happens if we cut at different angles? We cut at 5 degrees, 10 degrees. So what happens is those stresses start to change, right? Okay? Now, what I want you to do is sort of pay attention to the green lines. The red lines are the normal stress. The green lines are the shear stress. See how at certain angles they're getting smaller, and then about right there, they're 0? See that? See my shear stress? I tried to pause it, but there's a point when the shear stress gets to like 0. Somebody was writing on the screen. It wasn't me. I don't know. With a pencil. I don't know how that works. All right, but there is a point when the shear stress becomes 0, right? Yeah, I get distracted a bit. There's a point when the shear stress becomes 0. Now, I'm not going to try and start re-deriving Moore's circle for you, but the nice thing about the formulation is that when the shear stress becomes 0, the normal stresses reach their maximum, okay? And so that's really the benefit of Moore's circle, is that it determines what's the maximum possible normal stress, and that happens when the shear stress equals 0. So how do you formulate Moore's circle? You do some trig, and you take the derivative as, the shear stress approaches 0, or that's basically it in a nutshell. So these formulas that you plug and chug, that's what you're doing. You're just taking the derivative and determining what's that maximum principal stress. It's that simple. Now, I have a stress state right here. What is most nearly the maximum shear stress? Well, from that stress state, Moore's circle will tell us what is the maximum principal stresses and what's the maximum shear stress. Okay? Now, how does that come about graphically? Well, you all should know by now that if I start cutting things at an angle, I'm talking about trig, right? And you all should know that trigonometry and the graph of a circle are very closely intertwined, right? They're, you know, the unit circle, the coordinates of the points along that unit circle are the sine and the cosine, right? That should be common by now. Well, when you draw Moore's circle, the x-axis is your normal stress, the y-axis is your shear stress, and so if you got a circle, something like that, that actually wasn't bad. This point and this point right here are your maximum principal stresses. This is maybe sigma 1 and sigma 2, 2. And as for your maximum shear stress, well, the maximum shear stress is whatever that value is right there, but another way of saying that is it's just the radius of the circle, okay? So how do you determine that? Because you know, I know ultimately probably what you care about is the plug and chug expression. Hold on. Keep in mind it's here. Moore's circle. Here's the Moore's circle. There's the center. There's the radius. So it's just plug and chug. Sigma x minus sigma y squared over tau xy squared, square root of all that. Basically just a Pythagorean theorem. So tau max is the radius, which is one of the beauties about the formulation is that it's actually independent of the orientation. You could plug in any stress state and still get the same answer, like, you know, from orientation to another. And so what is that? Yeah, like 199.4, something like that, so the 200. This, I know we're running short on time. This next problem will be quick, though. I'll do my best to try and go through that quickly. Does that make sense? Any questions? So again, Moore's circle, don't let it scare you away. This is a very popular problem on the exam, giving you a stress state, determining something about it. Okay. Last problem. I have a rectangular steel bar, 37.5 millimeters wide, bless you, 50 millimeters thick, pinned at each end. It's subjected to axial compression. The bar has a length of 1.75 meters. The modulus of elasticity is 200 gigapascals. What's the buckling load? Okay. Now I'm going to do a couple things a little differently with this problem. The first thing I'm going to do, and this is just to sort of change it up a bit, is I'm going to let my force be kilonewtons and my length be millimeters. Because if you take kilonewtons over millimeters squared, that is a gigapascal. Okay? So the nice thing about that is my length, so like the length I'll have to change. That's 1.75 meters or 1,750 millimeters. But other than that, everything else that's in this problem, I can leave the way it is. The E is in 200 gigapascals and what have you. Pretty simple. Okay. Now, this problem is asking for the buckling load. Does anybody remember the formula for the buckling load? Okay, now what you're saying, pi squared E divided by KL over R squared, that's the buckling stress. The buckling force is going to be pi squared EI over KL squared. Now, so one is a buckling force, the force that causes buckling. The other is the stress that causes buckling. All right? Now, one question I do want to ask is, does anybody remember what K is? Now remember, K is the effective length factor. A hint, we are dealing with a column that's pinned on each end. So remember what K is when it's pinned? 1, right? That's what I like to hear. Remember, it only changes if you have different boundary conditions, like if it's fixed or what have you. What's that? Yes. Yes, it is. Yes. There's also one in the steel design section as well. So it is in there. Now, the only thing that takes some thinking is the moment of inertia. Now, this is a rectangle, right? So it's BH cubed over 12. So tell me what to write. What's B? And what's H?
B is 37.5.
Mm-hmm.
And H is it 1750?
No. H is just going to be the cross section.
Okay.
So B is 37.5 and H is 50, right? No. Okay. Here's why. No. This is a very common thing to do on these problems. But let's think about steel design for a second. If you have a column that is equally braced on each end and loaded in axial compression, about which axis will it buckle? The weak axis. Remember that? Remember the weak axis, right? How do you know which is the weak axis and which is the strong axis? The weak axis has a lower moment of inertia, right? So if I was looking at this cross section, IX would be 37.5 times 50 cubed over 12, but IY would be 50 times 37.5 cubed over 12, right? Remember, you flip the dimensions to get the moment of inertia about the other side. So if we just have a column that's being bent, it's going to buckle about the worst case scenario. And the worst case scenario is not going to be 37.5 times 50 cubed. It's 50 times 37.5 cubed. You remember that? So that's an easy thing to mix up. Okay? So this is going to be 50 millimeters, 37.5 millimeters. Weak axis. Okay? And so I'll help you out with that. This is a really big number. I think it's like 2.197 times 10 to the 5th millimeters to the 4th. Did I get that right? Somebody follow along with that? And so pi squared, 200, and then 2.197 times 10 to the 5th millimeters to the 4th over 1750 millimeters squared. And so when you plug and chug, that'll be something like that. Apologies, I know it's like 5:42. I don't like keeping you over too long, but I figure we were so close, it's like, let's just chug it out. What do you think? I got a quiz uploaded on mechanics. It's got 8 problems, but it's got a good bit more time on it. I think that one's listed, so it's like 30 minutes. So it's 30 minutes, so it's more time per problem. So, sound good? That's all I got.